Hello everyone, my name is Pou-Chun. I'm a master student from National Chieh-Chih University. Today, I'm great to present our paper, a normal distribution transform-based radar odometry designed for scanning and automotive radars. It is done together with Chieh-Chih Wang and Wen-Chieh. At the starting point, I would like to mention the motivation of this work. Unlike LiDAR and camera, radar has been shown as a reliable sensor that is robust in all weather conditions, which is important in autonomous driving. Therefore, radar is a sensor with a lot of potentials. On the other hand, radar sensors could be categorized into automotive radars and scanning radars. The automotive radar only provides sparse and highly confident features with relatively low accuracy and resolution, and each feature provides the Doppler velocity information. In contrast, scanning radar provides raw power range image, which is dense and with relatively high accuracy and resolution, but without the Doppler velocity information. So in this paper, we propose a first radar odometry adapts to both automotive and scanning radars. Our approach is simple yet efficient and outperforms prior art. We test our radar odometry on both NewSync and Oxford Robot Car dataset, which provides automotive and scanning radar data respectively. With respect to previous work, our automotive radar odometry reduced 51% of translation error and 17% of rotation error. And in scanning radar odometry, our approach reduced 30% of translation error and 29% of rotation error. Also, we show that our radar odometry achieves centimeter-level accuracy as LiDAR odometry does. The main challenge in automotive radar odometry is the sparseness issues. Radar odometry only outputs sparse radar point, and due to the low resolution, the radar point on same object might not at the same position when the viewpoint changes, which make data association become challenging. Unlike automotive radar, without doing any pre-processing, the raw radar scan provided by scanning radar includes serious noise effect, which is also challenging for radar odometry computation. In this slide, we will give the overview of our system. For automotive radar scan, we propose the probabilistic sub-map to handle the sparseness problem. And for scanning radar scan, we simply apply a threshold to remove part of the radar noise. In the end, to achieve radar odometry, we use a normal distribution transform-based method to match the consecutive preprocessed radar scan. First, let's talk about the probabilistic sub-map. In automotive radar scan, each radar feature has the radial velocity measurement that computed from Doppler information, as shown in the video. Under the assumption that most of radar measurements are static objects, by using RANSEC, we can remove most of the outlier and inference the ego velocity of ego vehicle. Next, in order to construct dense information from sparse automotive radar scans, we use the ego velocity integration to combine multiple radar scans into a radar submap. It not only builds a dense radar scans, but also handles the occlusion problem. In addition, we take the uncertainty of both radar measurement and ego velocity estimation into account to generate the probabilistic radar submap, which presents as a Gaussian mixture model. As shown in the video, our method successfully constructs a denser radar scan from sparse radar scans. Now let's talk about scanning radar. The raw range power image provided by scanning radar is noise included. Three typical types of radar noise are sparkle noise, receiver saturation, and multipath reflection. However, we found that most of radar noise has relatively low return power. Therefore, we simply apply a threshold to remove the measurement which is likely to be noise. As you can see in the video, the thresholded radar scan removed most of the noise, but the noise having higher return power is remaining. This noise is supposed to reject by the following process. After the preprocessing of two types of radar, we use the proposed probabilities weighted NDT to match consecutive radar scans. I'll call it PWNDT for short in the following presentation. The PWNDT divides radar scan into small grids and compute a normal distribution of each grid to describe the structure of environment according to the return power and uncertainty of the radar measurement in that grid. Next, the transformation between two scans can be obtained by finding the optimal solution that maximizes the overlapping scores. To be noticed, by setting a reasonable grid size in PWNDT, our method can handle the outlier effect that remains in the preprocessed radar scan. In the following slides, I'm going to talk about the influence of several parameters in our system. Let's get started with the first parameter, which is the number of scans used in the Probabilities Sub-Map, N. In this figure, the first row shows the submap and the second row shows the PWNDT cost map with different N settings. The color from red to purple represents the cost from high to low. The horizontal axis represents the forward-backward movement, and the vertical axis represents the rotational movement between two radar scans. The white circles and cross represent the ground truth transformation and the global minima of the cost map respectively. It is clear that when n equals to 1, where we only use the single radar scan, the global minima of cost map is not the ground truth transformation. This is because the single radar scan is too sparse to represent the shape of the environment in PWNDT. On the other hand, once we build the probability submap, which is, we said, n bigger than 1, the global minima and ground truth are well aligned. Let's take a look at the influence of odometry performance with different n settings. We found that setting n bigger than 1, the translational error dropped dramatically. However, the rotational error also increased slightly as n grows. This is because we use ego velocity estimation to build the submap. As n increases, the performance of our algorithm gets closer to the performance of ego velocity estimation, which is shown in green in the figure. Here, we also compare the performance of ICP and PWNDT with different n settings. When n is bigger than 1, our PWNDT always outperforms ICP because it takes uncertainty into account. Besides, we found that our method has smallest translational error at n equals to 3. Then the error grows as n increases. The reasonable explanation is that the quality of probability submap is highly dependent on the uncertainty estimation of ego velocity. So as n increases, the error of uncertainty estimation also increases, which makes the performance of PWNDT and ICP get closer. Next, let's move to the parameters for scanning radar. The first one is thresholding. The top figure shows that raw radar scan and thresholded radar scan, and the bottom figure shows the PWNDT cost map with different threshold value. When the threshold value is too small, a lot of noise remains in the radar scan, which makes the global minima of the cost map do not align with the ground truth. As the threshold value increases, the global minima of the cost map starts to align with ground truth, and the convergence spacing becomes narrower, which is better for PWNDT to converge to the precise solution. But when the threshold value is too big, which removes most of the measurement, the global minima will no longer align with the ground truth once again. We found that a threshold value around 0.2 to 0.3 is proper on Oxford dataset, where the data were collected in urban scenes. We also try to know the influence of odometry performance with different threshold settings. In this figure, we show the average frame-by-frame error using different threshold value, which means the average error of each consecutive scan matching. The result shows that our method is not much sensitive to the threshold value if the value is in a reasonable range. In the test threshold region, The maximal difference of errors by using different threshold values is only around 0.01 meter and 0.02 degree. The other parameter of scanning radar is the return power shifting. The figure on the left shows the one-dimensional range power example, and the figure on the right shows the corresponding normal distribution. Red data is the original data, and green and blue data is the data after power shifting. After power shifting, our method relies more on the data with high return power, which makes the normal distribution becomes narrower. From the normal distribution map and the PWNDT cost map, we can see that after power shifting is applied, the shape of the normal distribution is more clear, and the convergent basing of the cost map is narrower, which benefits the optimization position. Also, the experiment shows the error successfully reduced about 40% after applying power shifting. The experiment shows that our radar odometry outperforms the previous automotive and scanning radar odometry method. In addition, we show a comparison between the proposed radar odometry and the LiDAR odometry achieved by consecutive ICP scan matching. Both the automotive and scanning radar odometry achieve centimeter level accuracy as LiDAR odometry does, and the automotive radar odometry shows competitive accuracy with scanning radar odometry, although the automotive radar is with relatively low accuracy and resolution. However, we cannot precisely compare automotive and scanning radar odometry, because the two datasets have different scenarios and ground truths of reference odometry. Thank you for your attention, and please feel free to contact us if you have any question.